So again, this kind of control is not preferable, because when it operates during the operation, it operates on a linear mode here. Means that at any point, maybe this is the point here, so we shall have a P loss of VCE here times the ICE here, ICQ, sorry. So maybe at a higher voltage output of here, point here, so we have a VC of at this point and the ICQ at this point. So still we have a losses, regardless any voltage that provide or delivered to the load here. So there shall be a losses on the switch of VCEQ times ICQ. The advantage is that this kind of circuit which use BJT, it can provide by automatic control. Means that the circuit here will detect the amount of current. When the higher current flows, so the higher the amount of current that induced to the base is modified. So it maintain the voltage at this output, at the output of the load. But still, the inefficient operation of the system due to the linear mode will limit in terms of the amount or the size of the load that being applied to the system. So rather the system be used in terms of 100 watts, less than 100 watts, maybe 50 watts and below. If you use higher watts of load to provide higher watts of load, so the losses is not compromised. It's not preferable to, means that the efficiency is very low, so usually it's not being selected as the way how to supply the load using this linear mode of regulator. Then why recently we moved into switch mode converter is that we are benefiting in terms of the region here. So this is the region of fully switch on. This is the region of fully switch off. So we use the mode of on and off. Either we totally on, which we provide the highest current with a 0 voltage drop, or we provide the switch off mode, which is at the highest voltage blocking at 0 current flow to the circuit. So during switch off, the current is 0 ampere. During switch on, the current will be at full voltage, current amount that draw by the load. During switch off, the voltage will be full block. So V in here will be fully blocked by the device. So this is the switch that provide the fully on or fully off. So we have Q1 and Q1 ideal. Ideally, when it switch on, there will be no voltage drop across the switch. But in actual or practical switch, there still will be a voltage across your, leakage voltage across your switch. And during switch off, by right, if ideally there will be no current that flows into the circuit, but in practical there still be a leakage current and during on and off. But the system we are providing now, discussing now, is the switch mode converter, which use either fully on or fully off, and fully on or fully off. Just now we use linear mode, but this one is fully on, which at certain this is time voltage fully on, the voltage across the load at on or at 0. Then next cycle on and 0. So the transistor operates as electronic switch by completely on or off, switch on or switch off. So ideally the power loss is 0, and ideally when on or when off, there is no leakage voltage, there is no leakage current, but in practical there will be still a losses. The efficiency should be at 1 regardless any kind of voltage duty cycle. So the total T here, so any cycles should be, the efficiency is the same. Efficiency is the same. P in is the amount, the P out is the amount of P in that delivered to the load. Just now when we use our linear, so we can see that the losses is like this. Means that at 50% it pick up and plummeted at the 50%. But when you deliver at 100% of voltage, so it will reduce to 0. But for switch mode kind of converter, so the efficiency is maintained at 1. Means that there's no losses practically. Ideally. So for switch on and off, or for switch on and off, fully on or fully off just now, switch mode regulator, there will be a option of BJT, MOSFET, GTO, IGBT. All are the kind of variance transistor compared to the normal transistor. Okay, so the output in terms of average output is equal to I over T, and we integrate between 0 to the full full period of the conversion of the process. So it becomes the amount of duty cycle, D is the duty cycle, times V source. So the V source amount times the duty cycle, means that this is the full cycle of the process or the supply. So maybe at 50%, so 0.5 of Vs. So D is duty cycle, V times your Vs. So in terms of RMS, so D surge by 2 times your Vs. So P equal to I square R or P equal to V square over R. But when we involve the duty cycle in terms of manipulation, so it will be D or duty cycle times V square over R. So this is the amount of your average RMS and input power to the circuit. So in terms of control of DC converter during this duty cycle approach, so the duty cycle can be varied from 0 to 1, means that from 0 to full cycle of the process. The simplest control, so this is the simplest control using pulse generator or timer to produce a set of pulses with a fixed width and amplitude voltage. So the width here, the magnitude is Vs, but the width is will be manipulated or provided by the simple pulse generator or timer. So another control that duty cycle can be produced using constant frequency, whereby we can fix the frequency, but we modify the width of your pulses, so it becomes pulse width modulation control. And another kind of control is that we use we modify in terms of the whole period here. We can squeeze or we can expand, so it will be so-called frequency modulation control. Okay, in terms of pulse width modulation control, so the pulses here will be generated and delivered to the gate, delivered to the gate. So the pulses delivered to the gate. But how actually the pulses being generated is by we comparing the carrier and the reference. We have a comparator here in the circuit of control circuit, carrier compared to the reference. So the reference is a simple DC voltage. Meanwhile, the carrier is your sawtooth kind of signal, and sawtooth kind of signal. So the carrier will be sawtooth type of signal. So we shall compare with the DC from the reference. So when we adjust the reference voltage here, lower or higher, actually the intersection that happen with the carrier signal will be adjusted. Sorry. So means that if we intersect at lower voltage level, so the pulses will be modified. If we put a higher voltage level, so the pulses will be adjusted accordingly. So what happens that when we have a, let's say our sawtooth, the sawtooth signal will be maintained, but only the reference signal will be adjusted lower or higher. So the reference here will be adjusted, carrier will be maintained, the sawtooth will be maintained. So let's say during intersection of from lower to higher of your sawtooth signal, intersect here, what happens that it will give the signal to the output. We compare and we add the output to produce a zero to stop. When in intersect between higher to lower, reduce from higher to lower voltage, intersect with the V reference, or V reference is higher, means that V reference is higher compared to the carrier, so you have a higher output. V reference is lower, so you have a zero. V reference is higher, so at higher V reference higher, so there will be a positive or a 1 output. V reference is lower to the carrier, so there will be a 0 or lower output. So there will be 1 and 0, 1 and 0, 1, 0. The gating here will produce the pulses, and the pulses will be delivered to the gate or on the signal input panels or input pin to the power switch. So in terms of duty cycle, the amount of duty cycle is referred to the how much the T on here compared to the total duration or total period of the one cycle time. So total time is T, so the amount of T on is referring to the how much duty cycle provided by the signal. And the total time is amount of T on plus T off. This is T on, this is T off. And the modulation value, or the D here, is referring to the how much the magnitude of V carrier and compared to the V reference. So V carrier compared to the V reference. So the higher V carrier, we shift higher the carrier, so we shall have a higher carrier, we shall have a bigger modulation value. Assume that we have a carrier here at this level, so instead of the width of this point, so the width of the signal will be at this point. Sorry for the drawing, my pen is not so precise. So it means that we have a modulation value of higher point. See, so we come here. Let's say the value of your VR is reduced down to here, say. So means that your intersection will be over here. So the width of your signal will be like this, and so here and also here. So it will be thinner, and your width will be thinner. So this is the term of B, T, and M.